In relativistic and ultrarelativistic laser-solid interactions, particle-in-cell (PIC) simulations are essential for modeling kinetics-dominated plasmas. However, as the laser intensity transitions from relativistic to subrelativistic, specifically when the dimensionless vector potential A0 approaches 1, the limits of available modeling capabilities are reached. This necessitates the establishment of standardized testbeds for theoretical and experimental benchmarks. To address this, a novel testbed is developed to experimentally benchmark PIC simulations using a laser-irradiated micron-sized cryogenic hydrogen jet target. Time-resolved optical shadowgraphy of the expanding plasma density is employed, complemented by hydrodynamics and ray tracing simulations, to determine the bulk-electron temperature evolution after laser irradiation. The authors present a study of isochoric heating of solid hydrogen induced by laser pulses with a dimensionless vector potential of A0 approximately equals 1. By comparing the bulk-electron temperature of the experiment with systematic scans of PIC simulations, they demonstrate that the initial surface density gradient of the target is crucial in achieving quantitative agreement at 1 ps after the interaction. High-intensity laser-solid interactions have numerous applications, including fast ignition in inertial confinement fusion, laser-driven ion acceleration, and the investigation of warm-dense matter. To gain insight into the microscopic interaction picture, numerical modeling through simulations is often used retrospectively to guide the analysis and interpretation of exploratory experiments. The technical realization of optimal laser-target interaction conditions and the further development of available simulation tools to correctly capture all occurring physical processes during the transition of the target from an initially solid state to an ultrarelativistic plasma state are key aspects. State-of-the-art modeling of ultrarelativistic laser-solid interactions with petawatt-class lasers is currently based on a staged approach of numerical simulations. The testbed platform is designed to experimentally benchmark PIC simulations of high-intensity laser-solid interactions by measuring the bulk-electron temperature after isochoric heating of solid hydrogen. It utilizes a Draco 150 terawatts laser at the Helmholtz Zentrum Dresden-Rossendorf, featuring a 37 fs pulse duration and a central wavelength of 800 nanometers. The laser is focused onto a cryogenic hydrogen jet with a mean diameter of 4.4 micrometers. The experiment involves a time delay scan of two-color shadowgraphy in the tens of picosecond timeframe to determine the electron temperature evolution. This is achieved through a combination of hydrodynamic simulations, ray tracing simulations, and a Chi-2 fit of the simulated to the measured shadow diameters. The HDRT fit derives the best matching hydrodynamics simulation and the corresponding electron temperature evolution, providing a benchmark for PIC simulations. The experimental setup for this study involves a 37 fs pump laser with a peak intensity of 1.6 times 10 to the 18 W per square centimeter interacting with a cylindrical hydrogen jet target. Time-resolved high-resolution shadowgraphy utilizes a single microscope and two simultaneous backlighters, featuring pulse durations of 260 fs and 160 fs for 258 nanometers and 515 nanometers probes, respectively. The pump probe delay is variable, with a temporal resolution of 175 fs, and the captured data is blurred by the pulse duration. The electron density of the fully ionized target is 5.2 times 10 to the 22 cc, which corresponds to 30 times the critical plasma density of 800 nanometers light. The laser-target interaction is investigated through time-resolved off-harmonic optical shadowgraphy at a 90-degree angle to the pump laser propagation direction. Both probe beams feature pulse energies of approximately 0.3 microjoules and 5 microjoules, respectively, and pulse durations of 260 fs and 160 fs, respectively. Dispersion effects in the beam path cause a fixed delay of 4.6 ps between both probelaser pulses. All delays are given with respect to the arrival of the pump laser peak on target at 0 ps delay. To reduce the influence of parasitic plasma emission, both probe beams are focused by AF-10AP. A long working distance infinite conjugate microscope objective is used to image the shadow of the target simultaneously for both wavelengths, i.e., at two different ranges of plasma density. The two images are separated by a dichroic mirror and recorded by different cameras, each equipped with the corresponding color filters. Exemplary shadowgrams of a time delay scan as recorded by the 258 nm probe are shown in Figure 1b, with the pump probe delay given in the upper right corner of each shadowgram. The shadow diameter d258 nm_e is measured between the cyan arrows. For a 30 ps delay, volumetric transparency is observed. The spatial extent and fluence of the parasitic plasma emission vary from shot to shot. Figure 2a presents the measured shadow diameter from two-color optical shadowgraphy and HDRT fit to the experimental data. Figure 2b shows the total chi-2 distribution between the experimental data and all HDRT simulation data. The paper explores the evolution of a plasma in a high-density hydrogen target, utilizing hydrodynamics and ray tracing simulations. It begins by detailing the experimental setup, which consists of a pump laser, a probe laser, and an imaging setup for shadowgraphy. The target is a hydrogen jet, and the pump laser heats the target to create a plasma. The authors measure the shadow diameter as a function of pump probe delay, observing that the diameter increases with delay until volumetric transparency occurs. The authors then detailed their hydrodynamics simulation using the flash tool with a two-temperature adiabatic expansion model and the hydrogen equation of state FPEOS. They used three free parameters: the initial ion temperature T0, the initial electron temperature T0, and the initial plasma diameter D0. The initial ion temperature is assumed to be 10 electron volts, and the authors perform simulations with different initial electron temperatures and plasma diameters. In addition, the authors conduct ray tracing simulations to model the shadow formation of each probe beam. They calculate the refractive indices from the local electron density and simulate the experimental imaging setup using Zemax software. The resulting shadow diameters, d258 nms and d515 nms, are derived at half of the unperturbed background intensity. The authors compare the simulated evolution of the shadow diameters with the experimental data and find that the best matching hydrodynamic simulation occurs when the initial electron temperature is 250 electron volts and the initial plasma diameter is 3.5 micrometers. This simulation accurately predicts the observed volumetric transparency at certain delays for both the 258 nanometers and 515 nanometers probes. The paper concludes that the combined hydrodynamics and ray tracing simulations provide a comprehensive understanding of the plasma evolution and shadow formation in high-density hydrogen targets. Hydrodynamics and ray tracing simulations were performed to investigate the behavior of a target bulk at zero radius versus time and the refraction of probe rays. The simulations focused on the radial electron density, electron and proton temperature, and refractive index distribution. The results showed that the radial electron density and temperature profiles exhibit distinct features, such as a central plateau and an outer slope, which are sensitive to the initial plasma conditions. Experimental data was obtained by varying the initial plasma diameter and electron temperature. The chi-2 variance was calculated to evaluate the difference between experimental and simulation data. The minimum chi-2 values were reached for specific cases, indicating better agreement with the probing data. For instance, the chi-2 value decreased significantly when the initial plasma diameter was increased, suggesting that the simulation accurately captured the plasma expansion dynamics. The HDRT fit method was employed to analyze the experimental data, allowing for heuristic electron temperature evolution. This method was applied to the presented experimental data, providing insight into the plasma dynamics and refraction properties. The results demonstrated the effectiveness of the HDRT fit method in reproducing the experimental data, highlighting its potential for diagnosing high-energy density plasmas. The authors compare the results of a testbed and a particle-in-cell (PIC) simulation of high-intensity laser-solid interaction, focusing on the temporal evolution of the bulk-electron temperature. The PIC simulation, performed using the 2D3VPIC simulation tool PI-CON-GPU, models a fully ionized spherical hydrogen column with a density distribution described by equation 4. The laser pulse is incident along the y direction, polarized in the x direction, and features a Gaussian shape in space and time with a pulse duration of 37 fsfWhm and a laser spot size of 14 micrometers fWhm. The simulation box has a size of 32 × 32 square micrometers with absorbing boundary conditions, and the simulation uses a cell length of 0.8 micrometers, 96 and 240 macroparticles per cell. A relativistic binary collision mechanism is also included. Figure 4a shows the spatial distribution of the electron density in the PIC simulation for different delays, with 0 ps delay corresponding to the arrival of the pump laser peak on the front side of the target. The comparison between the blue and orange lines in Figure 4a indicates that the electron density at 0.2 ps delay does not significantly differ from the initial state at 0.1 ps. Figure 4b displays the spatial distribution of the electron temperature at 1 ps delay. The temporal evolution of the equivalent temperatures Tn is shown in Figure 4c, where thermalization is reached at around 1.5 ps. Notably, the PIC simulation captures the processes of isochoric heating and thermalization of the bulk electrons, which are not captured by the hydrodynamics simulation of the HDRT fit. Both simulations ultimately lead to the evolution of the bulk electron temperature after thermalization, which can be compared to the hydrodynamics simulation of the HDRT fit, as shown in Figure 4d. The authors of the research paper investigate the expansion of hot electrons into the surrounding vacuum at densities below 0.1 N 800 nanometers C. By analyzing electron density profiles at 0.2 ps, 1.0 ps, and 2.1 ps, they identified two characteristics: a temporally increasing exponential scale length of the plasma density, driven by adiabatic expansion, and a transiently occurring step of the density profile caused by the thermal pressure of the coronal plasma. The spatial distribution of the electron temperature T at 1.0 ps delay shows a spatially constant temperature of 450 electron volts inside the bulk plasma and temperatures above 10 keV in the coronal plasma. The hotter coronal plasma expands faster than the bulk plasma, and the influence of the coronal plasma on plasma densities decreases with delay. The authors also present the temporal evolution of the bulk electron temperature T and equivalent temperatures Tx, Ti, and Tz, which are calculated from the average kinetic energy of the electrons within the bulk plasma. The maximum of Tx and Ti of 20 keV is reached at 67 Fs, indicating isochoric heating of the plasma bulk. Subsequently, the temperatures Tx and Ti decrease, while Tz increases, and the plasma thermalizes within about 1.4 ps after the termination of heating. The thermalization time is in close agreement with the analytic electron-electron collision rate of hot electrons. The authors compare the evolution of the bulk electron temperature T of the PIC simulation with the electron temperature evolution of the HDRT fit to the experiment, showing that both approaches are comparable only after thermalization, i.e., at delays later than 1.5 ps. The authors discuss the feasibility of the testbed to benchmark PIC simulations, highlighting the effect of different parameters of the PIC simulations on the chosen endpoint of the bulk electron temperature after thermalization. They also mention the importance of considering resonance absorption, vacuum heating, and preplasma effects on laser absorption efficiency. The PIC simulations presented on this page focus on the electron velocity distribution and bulk electron temperature, revealing a significant decrease in the latter as the surface scale length L0 increases. This decrease is attributed to a change in the laser absorption mechanism from vacuum heating at low L0 to resonance absorption at high L0. The electron velocity distribution shows a decrease in forward-moving electrons for higher L0, indicating this transition. The total temporal peak of the forward-moving electron current also decreases with increasing L0, contributing to the reduction of the bulk electron temperature. An analytic calculation of the electron temperature increase by resistive return current heating based on the simulated forward-moving electron current demonstrates good agreement with the increase of the bulk electron temperature up to 70 Fs delay. The results suggest that the decrease of the forward-moving electron current contributes to the reduction of the bulk electron temperature as the laser absorption mechanism changes. The PI-CON GPU simulation results demonstrate that the low-temperature collision correction has a negligible influence on the bulk electron temperature after thermalization. The study investigates the influence of the analytic uncertainty of the Coulomb logarithm, revealing a decrease in the bulk electron temperature with decreasing Coulomb logarithm. This effect is small compared to the dependence on the initial surface density scale length. Systematic PIC simulations show that the initial surface density scale length primarily contributes to the overestimation of the bulk electron temperature. The observed transition over different heating mechanisms of electrons confirms previous work at similar laser intensity levels. The importance of the exact initial distribution of the target density in PIC simulations is highlighted, particularly in laser-driven proton acceleration. The testbed is ready for controlled parameter scans, investigating the transition from thermal-driven to hot electron sheath-driven plasma expansion, and can be modified to probe near-infrared wavelengths for density measurements and PIC simulation benchmarking. It also discusses the potential for studying multi-species mixtures, cryogenic argon jets, and the use of extreme ultraviolet backlighters, as well as combining with laser-driven secondary sources for isochoric heating. The authors acknowledge the Draco laser team for their support and measurements, as well as the partial support from H2020 LaserLab Europe v. The experimental setup of the optical microscope is outlined, featuring a magnification of insert magnification, a spatial resolution limit of insert resolution, and camera specifications of insert camera details. The use of distinct probes for imaging is highlighted, including 258 nanometers and 515 nanometers probes, each with their respective camera configurations. The measurement of the initial target diameter is also described, involving the evaporation of liquid hydrogen and the expected initial diameter of the solid hydrogen jet. In the appendix, the HDRT fit is discussed, relying on two fundamental assumptions: homogeneous initial temperature and isochoric heating. These assumptions are crucial for the fit, which plays a vital role in the research. Dynamic simulations are conducted to calculate the plasma expansion process, beginning with the calculation of the Knudsen number, which indicates that the system is within the applicable range of hydrodynamics equations. The thermal velocity of electrons and mean free path length are calculated, revealing a weakly coupled plasma. The Debye length further confirms the plasma is weakly coupled, as the plasma parameter is greater than 1. The PIC simulation results in magnetic fields ranging from 1 T to 100 T and ion temperatures between 10 electron volts and 100 electron volts. The simulation tool Flash is used for high-energy density physics, with uncertainties mainly arising from the hydrogen equation of state and the assumption of two-dimensional radial symmetry. An appendix discusses the equation of state of hydrogen, comparing different EOs, and the ionization state of the target, including laser contrast measurements. Additionally, an appendix on radiative cooling estimates energy loss by radiative cooling, showing Bremsstrahlung radiation as the main mechanism. Figure 6 compares the isotherms of four equations of state: EOS, sesame EOS, FPEOS, FEOS, and flash EOS for hydrogen at electron temperatures of 10 electron volts, 100 electron volts, and 1000 electron volts. The electron density profiles at 10 ps, 20 ps, and 30 ps are also compared for sesame EOS and FPEOS, with initial conditions of T0 equals 300 electron volts and D0 equals 4.4 micrometers. The authors then estimate the influence of radiative cooling by calculating the energy losses from the bulk electron temperature evolution using the results of the particle in cell PIC simulation from section 3. There are three main types of radiation: bound-bound, free-bound, and free-free radiation. The bound-bound radiation, PIR, is given by equation F1, which accounts for radiation emitted from atomic ionization. The free-bound radiation, PRR, is given by equation F2, which accounts for radiation by electron recombination. The free-free radiation, phosphorus monobromide, is given by equation F2, as well, which accounts for Bremsstrahlung radiation by electrons. The total radiation loss, PR, is the sum of these three processes, as given by equation F3. By comparing equations F1 and F2, it is found that PRR is negligible compared to phosphorus monobromide, as the relevant bulk electron temperatures are in the multi-hundred eV range. For fully ionized hydrogen atoms, PIR is 0. Therefore, the total emitted power is approximately equivalent to the power of free radiation. Figure 7 illustrates the energy loss by radiative cooling, with the black line corresponding to equation F5. Calculations by FLYCHK are also shown, including bound-bound, bound-free, free-free, and total radiation loss. This section of the research paper delves into radiation loss mechanisms in high-temperature plasmas, with a particular emphasis on Bremsstrahlung radiation as the primary loss mechanism. The authors employ the temperature evolution from their PICLS simulation to calculate the total radiation loss, which is then compared with calculations derived from the non-local thermal equilibrium tool FLYCHK. The findings indicate that free radiation is the main contributor to radiation loss, aligning with previous studies. The radiation loss per electron is calculated to be 0.13 electron volts, a value less than 0.1% of the relevant thermal electron energies, thus rendering radiative cooling negligible in this context. A comparison between 2D 3V-PIC and 3D-PIC simulations reveals high agreement between the two before 100 Fs. However, after this point, the temperature in the 2D 3V case increases to slightly higher absolute values, resulting in a difference of approximately 14% between the two simulations between 200 Fs and 400 Fs. An additional section explores the low-temperature collision correction, which is not accounted for in the PIC simulations. By utilizing the hot electron scaling and the bulk electron temperature evolution equation, the authors estimate the influence of the low-temperature collision correction on the temperature evolution. This calculation provides an estimate of the impact of this correction on the overall results, thereby enhancing the understanding of the plasma's behavior. Figure 9a illustrates the electronian collision frequency versus electron temperature, with and without low-temperature correction. The current density of hot electrons, calculated using equation H9 from the PI-con-GPU simulation, is presented in Figure 9b. The electron temperature evolution, obtained from PI-con-GPU and calculated from the current density in Figure 9b, is shown in Figure 9c. The three heating terms on the right-hand side of the equation are diffusion heating, resistive return current heating, and drag heating. The electron conductivity, sigma T, is given by equation H10, which is a function of the electron density, electron rest mass, and electronian collision frequency. The electronian collision frequency, nu-A, is calculated using Spitzer's formula, as shown in equation H11. This formula depends on the average ionic charge, electron density, electron temperature, and Coulomb logarithm. In the PICLS simulation, a total amount of energy of 25% is absorbed from the laser, resulting in a total energy of 160 mJ and a hot electron temperature of 90.5 keV. The number of hot electrons generated by the laser-target interaction is calculated using equation H4, assuming all absorbed energy is converted into hot electron energy. This results in a total number of hot electrons of approximately 2.8 times 10 to the 12. The hot electron density is calculated by assuming a uniform distribution of hot electrons in the plasma column and laser spot, resulting in a density of approximately 1.29 times 10 to the 22 cc. The current density of hot electrons is then calculated using equation H6, yielding a value of approximately 2.48 times 10 to the 17 A per square meter. The fraction of temperatures generated by resistive versus drag heating and resistive heating versus diffusion heating are derived from Ref. 52, as shown in equations H7 and H8. These equations indicate that resistive return current heating is dominant for the heating of bulk electrons. Consequently, equation H2 is simplified to equation H9, which describes the evolution of the electron temperature. Overall, this page presents the calculation of electronian collision frequency, electron conductivity, and current density of hot electrons, as well as the dominant heating mechanisms in the plasma. The results are crucial for understanding the dynamics of hot electrons in the plasma and their interaction with the laser pulse. In the context of a hydrogen plasma, the electronian collision frequency is a crucial parameter to consider, particularly at temperatures below the Fermi temperature. This section delves into the low-temperature collision correction and its influence on the bulk-electron temperature. The effect of the Coulomb logarithm in PIC simulations is also explored, as it significantly impacts the energy transfer from laser-heated hot electrons to bulk electrons. The electronian collision frequency is calculated using equations H11 to H16, incorporating both Spitzer's formula for high-temperature collisions and phonon scattering for low-temperature collisions. Figure 9a presents the overall collision frequency, revealing a reversal trend below the Fermi temperature. The return current density is derived from equation H9, with the temporal iteration step I and the upper limit of T set to 50 fs. The retrieved current density of hot electrons is depicted in Figure 9b. The impact of the low-temperature collision correction on the bulk electron temperature is calculated and compared to the PIC simulation in Figure 9c. The results indicate that the low-temperature collision correction has a negligible effect on the final bulk electron temperature. In the appendices, the authors investigate the effect of the Coulomb logarithm in PIC simulations. Simulations are conducted with different fixed values of lane lambda between 3.5 and 15, resulting in changes in the bulk electron temperature from 1.25 keV to 1.5 keV at 1 ps. This variation highlights the sensitivity of the energy transfer to the Coulomb logarithm, emphasizing the importance of accurate collision models in plasma simulations. The 3D PI-CON GPU simulations investigate the effect of the hotelectron pressure gradient on the bulk electron temperature distribution within the laser spot region. A cylindrical hydrogen rod with a density of 30 N800 nmc is considered, without surface scale length. The laser parameters are equivalent to those in Section 3. The results show temperature gradients in all directions, with the temperature decreasing from 1.7 keV in the laser spot region to 1 keV above and below it, and from 1.7 keV on the front to 1.6 keV on the rear side of the target along the laser propagation direction. This is consistent with 2D 3VPIC simulations, which exhibit a uniform temperature distribution after about 500 fs. The study also calculates the dependency of the local bulk electron temperature on the local laser intensity and compares it to 3D PIC simulation results, showing that Joule heating by hot electrons is dominant for the heating of bulk electrons. The average bulk electron temperature variation along the z-axis in a 3D PI-CON GPU simulation is depicted in Figure 11. This variation aligns with the scaling I/R 0.4 within the full width at half maximum, FWHM, of the laser. However, beyond this region, the temperature scaling differs, indicating that the pressure gradient of hot electrons is relevant only outside the focal spot FWHM. To investigate lateral heat transfer by diffusion, three-dimensional hydrodynamics simulations were conducted. These simulations compared the plasma density on the tens of picosecond timescale for different initial temperature gradients. Utilizing the flash code, the simulation box was 20 micrometers in height and 20 micrometers in radius. Three temperature gradients were initialized: a uniform temperature distribution, a temperature distribution proportional to the intensity distribution of the laser I/R, and a temperature distribution proportional to I/R 0.4. The results of these simulations are presented in supplementary figures, demonstrating high agreement between the three-dimensional cylindrical symmetric simulations and the two-dimensional radial symmetric simulation. Small deviations of the density profiles occurred at densities below 0.1 N800 nanometers, amounting to a maximum of 5% for the case of an initial temperature distribution proportional to I/R. The overall agreement justifies the use of two-dimensional radial symmetric hydrodynamics simulations by the HDRT FIT. Laser-driven ion acceleration offers a promising approach to generating high-energy particles, with potential applications in radiobiology and nuclear physics. However, achieving high repetition rate experiments using petawatt-class lasers poses significant challenges. Advanced target technologies are essential to enhance ion beam quality and stability, and understanding the underlying physics of laser plasma interactions is crucial for efficient and reliable experiments. Recent studies have shed light on key factors influencing ion beam properties, including target geometry and composition, laser parameters, and plasma instabilities. Cryogenic jets have emerged as a promising target technology, enabling high repetition rate experiments through the use of mechanical chopper systems to control the flow of cryogenic liquids. This approach allows for more frequent laser shots and improved data acquisition rates. Advanced simulation tools, such as particle and cell codes, play a vital role in modeling and predicting laser-plasma interactions. These simulations are essential for optimizing experimental conditions and understanding the complex interplay between laser, plasma, and target properties. International collaboration and knowledge sharing are critical for accelerating progress in this field. Further studies are needed to investigate the radiobiological effects of laser-generated ion beams and their potential applications in cancer therapy and nuclear diagnostics. Despite significant advancements over the past 2 decades, continued research and development are necessary to fully exploit the potential of laser-driven ion beams for various scientific and medical applications. Ultra-short pulse laser interactions with solids are a topic of great interest in the field of high-intensity laser-solid interactions. Research focuses on laser acceleration of protons, transient laser-induced breakdown of dielectrics, and off-harmonic optical probing of high-intensity laser plasma expansion dynamics. Additionally, studies on isochoric heating of solid aluminum and the role of relativistic laser intensity on isochoric heating of metal wire targets are also explored. The dynamics of electron temperature scaling, ion heating, and collisional relaxation of superthermal electrons are also discussed. This comprehensive overview connects various studies, providing insights into our understanding of laser-solid interactions. The research papers discussed focus on astrophysical thermonuclear flashes, plasma physics, and high-power laser interactions. They highlight the development of new simulation codes, such as flash and extensible component-based architecture for flash, used to model complex astrophysical phenomena. Recent advancements in laser-driven ion acceleration, plasma wave dynamics, and the study of structural dynamics in nanoparticles under intense laser fields are also covered. The summaries emphasize the significance of these findings in understanding high-energy density matter and its applications.